Is the color okay?
Oh,
All right. Let me introduce you to the del operator. You guys heard of the del operator? It's this guy.
I'm a math.
All right. The del operator is an operator that can be seen as a vector. And you notice it looks like something, right? But it's missing something. It looks like the symbol that we've been using for the gradient, but it's missing something. Yeah, it's missing a function. But what I'm going to do is, we're going to take this off a little bit of the function and look at it as if it's its own standing definition. And the definition itself doesn't seem like it makes much sense without a function, but that's what operators are. Operators are things that apply to functions. So without the function, this could just be seen as d dx in the I component. I guess I should put plus if I'm using ijk. D dy in the j component. And then if whether this is three variables or not, we can still define d dz in the k component as a three-dimensional vector. Now this has no quantity. This is an operator like d dx. So examples of operators that we might have seen in the past is d dx, or the integral of something dx, right? They're there ready to work on something, and the something that you put in there is a function. And if we really want to get technical about it, things like plus, minus, they're all operators that operate on numbers or other things. But in terms of calculus, these are the operators that we're going to be concerned about. So notice that this is a vector. And so what we're going to expect is we're going to expect the rules of vectors to apply to this. Well, we're really going to focus on a couple of rules of vectors. Three. And let's take a look at the one that we're already familiar with. Let's take a look at the gradient. So let's let little f be, let's go R3. Be a scalar function. And this word scalar is important for us because it is a scalar. Now, this notation that we've used before looks like we're combining a vector, the del operator, and a scalar f, right? And so how do we deal with an operation like that? So scalar multiplication on a vector v, so v vector is equal to v1, v2, v3, and alpha is a scalar. Then alpha times the vector v is equal to, it's just distributing that scalar, right? So alpha v1, alpha v2, alpha v3. So I want you to think about the gradient as doing the same thing. We have a del operator that's a vector, and we have a scalar function f. So just think about this by definition as taking your scalar function f and then distributing it to each one of these components of the vector. So I'm going to change my notation, and I'm going to use the angle brackets to change, and then I'm going to say my partial with respect to x, that's my first component, my del operator, gets scaled by f, or this is like df dx. My second component in my vector, partial with respect to y, gets also multiplied just like the scalar multiplication, and the partial with respect to z gets multiplied. So then we have what we know of as our gradient. So I'm going to change notation again. So the sub x, remember, is the partial with respect to that variable, fx, fy, fz is our gradient. So it's the same gradient that we've seen before, except I'm reintroducing the gradient via this del operator now. Okay? So we're not going to think about addition or subtraction of this, but what other types of vector operations did we study? We did cross products and component projection. So component projection, I think that's a little complicated, but in terms of a direct operation between two vectors, the cross product is one of them, and what's the other one? The simpler one? The dot product. So let's think about dotting this del operator with another vector. Wait, I need a vector. Need a vector valued function, or what are we studying? No? Related. But
line integral.
what are we putting inside of a line integral?
No,
Vector field. So now we have a vector in the del operator and a vector in a vector field, and let's combine them and see what happens. What? Get a del field? Close. Well, actually, no, but. So let's take a look at the dot product first. So let's take our del operator and dot it with a function. Vector field. So it makes sense. It's a vector, and then the del operator is a vector, and one of the reasons why we created the del operator is because we want to look at it as an operator, a vector operator that operates on vectors, among other things. So let's take our del operator and make the dot product symbol of f. Oh, before we do that, sorry, I need to bring this down a little bit. Before we do that, we should specify what's in f. Now, this is where we can use different notation that might get a little complicated. So in 2 dimensions in Green's theorem yesterday, you saw P and Q. So if you go into 3 dimensions, it's kind of natural to go PQR. Some books call it little f1, little f2, little f3. So let's try to establish a notation and try to stick with it. What should we use? PQR or F? So PQR. Oh, and these are all individual functions of x, y, z. So P is a function of x, y, z. Q is a function of x, y, z. And R is a function of x, y, z. So a slight disadvantage here. R, sometimes we use that for a region or a rectangle. Now we're using it as a function. But as long as you know what the deal is, where its context is, then you'd be okay. All right, so we're going to dot them. Let's rewrite, or let's write the intermediate step here, where the del operator is the operator of partials with respect to x, y, and z in that order. And then we're going to dot it with, and I'm going to take off the x, y, z here, just say PQR. And so this is really just a partial. I can write it a couple of different ways. I'll use a Leibniz notation, the partial of P with respect to x, partial of Q with respect to y, and then the partial of R with respect to z. Or I could write P sub x, Q sub y, R sub z. But in any case, this is my dot product. And if you have 2 dimensions, then all that means that the 3rd dimension isn't there. So just a little note, if you were in R2, your vector field was 2-dimensional, then this is just partial of P with respect to x, partial of Q with respect to y. Oh, yeah, good point. Oh, sorry, my bad. You guys taking notes in pen? Well, I'm going to have to cross it out. This is wrong. Plus, your output should be a scalar, and it's a scalar function. Does this one look familiar? Is it Green's theorem? What's wrong with it? Green's theorem is subtracting, huh? So let's make a point of that our output here is a scalar. Scalar? Scalar. It's going to end up being a scalar function. Okay? So the formal definition of this is called a div, or divergence. Some of the possible notation that you might see, we've seen that this is really a dot product of the del operator and the vector field. Sometimes they actually write out the word div of f, and that's the partial of p. Well, I'm just going to rewrite what's up there. For 2 dimensions, you can stop where you need to stop. For 3 dimensions, you just go one more. Okay, so that's the div. So it's a del operator that acts on a vector field, and then you get some constant. Now let's do the other one, which is the curl. I mean the cross product. And let's see how that looks like. What? Yeah, well, instead of a dot product, you put a cross, and then we'll get a different result. So let's take a look at the cross product of this thing. And with a cross product, again, you need a 3-dimensional vector with a 3-dimensional vector. Suppose you could try to do it with a 2-dimensional vector. We've done that before with cross products, haven't we? Yeah, so the k component is 0 or something. Let's do the cross product. Again, we'll have a function, a vector field, R2 to R2, or R3, sorry, to R3. And so let's make some room here, because whenever we do the cross product, we need to set up like a matrix, don't we? So matrix is going to have an ijk component. Now this is kind of weird because this del operator is really just an operator. So I'm going to put partials with respect to x, with respect to y, and then with respect to z. And then I'll have my f, which is p, q, r, are functions of x, y, and z. All right, let's take this carefully. What's going to be an I component here? And the I component is partial of r with respect to y minus partial of q. By the way, if you guys are writing this down, you can use the shorthand notation, right? You just say q sub z if you want. So the j component is going to have a negative associated with it. So I don't know if you guys are used to putting the negative and then going through it like the diagonals minus the wings, or you can just keep this positive and go the wings minus the diagonals. I guess I'll use a negative sign like we've done with cross products. And imagine the I column getting crossed out. I have the partial of r with respect to x minus the partial of p with respect to z. And that's in the j component. And then in the k component, partial of, q with respect to x minus partial of p with respect to y. There's a minus sign here. That looks complicated. Now that's it. This is called the curl. So you can write it literally with the cross product notation, or you can actually write the word curl, F, to mean the same thing. Okay? Let's look at it in 2 dimensions. If your F is just P and Q, it's a 2-dimensional vector, and imagine we're going to cross two 2-dimensional things. And I guess I should have squeezed in x and y. These are functions of x and y. So let me rewrite that. Well, I'll just erase it. X, y. Why am I writing this? I don't know. So I'll make a point a little bit later on when we do the cross product. We'll see that there's no z's in here. So if you think about taking the derivative with respect to z, it'll just disappear. All right, so let's take the curl of this. And whenever we take the cross product, we assume that something's 3-dimensional. And if we're dealing with something that's 2-dimensional, we just kind of set the 3rd dimension equal to 0. So partial with respect to x, with respect to y, with respect to z, and then p for the x, q for the y, and 0 for the z for my function. Now the first one says I'm going to take the r, which is 0, with respect to y. Well, that's 0. And then now I take my q function with respect to z. So the partial of q with respect to z, because q doesn't have any z's in there, and I want to take the derivative with respect to z, that's going to be constant. So that whole thing's going to be 0, right? So I got 0 in the I direction, minus partial of r with respect to x. Again, r is equal to 0, so you take a derivative of that with respect to x, that's going to be 0. Partial of p with respect to z, that again is 0. So I have nothing in my j component. What's my k component? That's Green's theorem. Now it looks like Green's, huh? So it looks like Green's theorem involves a derivative after all. So we'll talk more about that later. But notice that this is, in fact, a vector. This is still a vector, so we want to make sure that we acknowledge that fact, that this is a 0, 0, and that thing as a vector. Okay. Any questions about the curl? I don't know. What? Curl? Because it curls. Should we do some examples? Or do you really want to know why it's called the curl? Let's do some simple examples first, and then we'll talk about the curlness of it. There's a couple of simple examples that people like to use, and the examples are two-dimensional, so you can imagine this thing happening in 3D also. But we'll do a couple of two-dimensional examples, and then we'll talk about the meaning of it, and then we'll go to 3D. Let's see, example 1, vector field, fairly simple vector field, x in the I direction and y in the j direction. And our example number 2 is going to be a vector field where we have negative y in the I direction and x in the j direction. So we've seen these vector fields before. In fact, this might have been the first 2 vector fields I gave as an example. So these are good vector fields to work with because they're nice and simple. Let's first take a look at the div. By the way, there's no gradient here, right? This is a vector function, so there's no gradients involved. So let's take the div first. Div of f. So it's a derivative of x with respect to x, partial of p, this is p, and this is q. So it's a derivative of x with respect to x plus the derivative of the q function y with respect to y. So it's a derivative of x with respect to x. One. And the derivative of y with respect to y is 1. So this is a div of 2. In some examples, you'll have functions here. Here we just have constant because we're looking at a super easy example. And let's take a look at the curl. Should I leave space here? I'm going to leave some space here to get a picture in. So the curl, since this is two-dimensional, I know my first 2 components are going to be 0, right? So I might as well just go ahead and put a 0, 0 there. And then now, for the last component, I want the derivative of q with respect to x. So the derivative of q is equal to y in this case, minus the derivative of p is equal to x in this case, the derivative of p with respect to y. So what is this? 0. So this is 0, 0, 0. Okay. All right. Well, I guess it's, yeah, it has to be a three-dimensional vector, so that would be zeros. All right, let's see what this next example. Let's take the div of this. So the div is the derivative of p with respect to x plus the derivative of q with respect to y. So p in this case is negative y. This is your p function. And then q in this case is your positive x. And what is the result going to be? 0. Okay, let's take the curl. So again, it's a two-dimensional function, so we can assume that the first two components are going to be 0. And now the third component, we want the derivative of q with respect to x minus the derivative of p with respect to y. So what is the derivative of q? 1. So this is going to be 1. And what's the derivative of p, the derivative of negative y with respect to y? It's negative 1. So what's our curl going to be here? So it's a vector, right? 0, 0, 2. So simple examples, we're coming up with constants, and for a more complicated example, or in most other examples, you might not have constants, you'll have functions. But in these two examples, it looks like it's going to be the same div for every point, same curl for every point. And let's see what this means. And for this, let's get a graph of a vector field, how the vector field might look like. So let's start with this vector field. Yeah, dx and dy. And then it's just going to be xy, right? And then I think we saw this before where the vector field looks like it just outward arrows. Maybe you got some 3D glasses on. So these are just arrows going away from the origin. Oh, I can't see the arrows, they're too small. You know? All right, let's try it again. Get a nice picture. Zooming in and zooming out doesn't help. Oh well. All right. The divergence is a way to measure how something is expanding. And what we want to imagine is on this vector field, imagine a box or something. And as you go through and follow a flow, your box is going to be expanding. Okay? So as you go along there, imagine that your box is expanding, and so when it's expanding, div f is positive, you have something that's expanding. And if the div is negative, then your particle is going to be compressing. So this is an expansion and compression measurement as you move along the vector field. So if we take that same idea and apply it to the next vector field, where our next vector field is negative y and x. We saw this picture before, didn't we? So it looks like in this particular vector field, we are not expanding or compressing. So if we follow along in this vector field a particular path that's running along the vector field, this is not expanding or compressing. So div f in this case is equal to 0. It's not expanding or not compressing. It's incompressible. Is that a word? Incompressible. Incompression? No. Incompressible? No. It's not being compressed or it's not expanding. Okay? All right. Curl. For the curl, what I want you to imagine is imagine a disk floating . And as your disk follows a specific path along this vector field, the curl measures the rotation, how this thing rotates. Okay? So how this rotates, this is a vector. How is this describing rotation? What's this? Well, he answered it earlier with this thing, the curl. So it handles the rotation using a right-hand rule. It's a three-dimensional vector. Think about a three-dimensional vector and a right-hand rule. Okay? Think about putting your right hand on this disk. So if it's not curling, then your thumb is just kind of down. If it is curling, the direction in which this is curling is going to point towards the direction of this vector. This is a vector, right? Three-dimensional vector. So it's going to move in that particular direction. Since this is 0, it's not curling, doesn't really make that good of an example. So let's go to the next one and see if we can measure the rotation, so to speak. So what we would do in this example is imagine that you have that disk with a little marking on it, and as you move along a flow line, take off my glasses here. That these disks are rotating. So they measure a rotation, and the direction in the rotation is perpendicular to this vector. So this vector is 0, 0, 2. On the xy plane, it goes straight up in the positive direction, right? So in the positive direction, these disks are curling or are rotating in a counterclockwise direction because it's positive. And so imagine putting your right hand on one of these disks, and which way is it rotating? It's rotating in a counterclockwise direction. So the vector itself is going straight out at you in the z direction. If this would have been a -2, then the rotation would have been clockwise, which means following your right-hand rule, if you put your right hand on one of these disks that's spinning clockwise, your thumb is going to be into the screen. So that would be a negative rotation, or opposite of what we have right now. It's hard to deal with positives and negatives when you're in 3D, but when you're in 3D, it makes a little bit more sense to talk about a rotation in space. So that's what they mean, yeah?
So what do you think is always
Counterclockwise is positive, yeah. Well, it depends, because when you're looking at it in two-dimensional, counterclockwise makes sense. But when you're in 3 dimensions, what does counterclockwise mean? Kind of depends on your point of view, right? Where you are. So, yeah, it could be a lot of different ways to think about it.
Like if you were solving a problem and you put your set of coordinates, did you do it that way? That's not like
Well,
so in physics we choose like data, like counterclockwise being positive or negative.
yeah.
But you also write down, you put a little arrow in the corner doing that, so you're designating where you're going to the problem.
I think it depends on your point of view. If your point of view is always going to be counterclockwise, is positive. If your point of view just happens to be from the other side, then it might be different from somebody else looking in from the other direction. Aaron?
Does the number affect the rate?
Yes, divergence and the curl. So here we have a divergence of 2, so your box is moving, it's expanding by 2 meters per whatever, per step. Here your rotation is 2. If your rotation is 4, then this is spinning a lot faster as you're moving along. Yeah. So this curl of 0 is kind of a big deal for us, and we'll talk a lot more about it. Curl of f equal to 0, and I have to say a vector, so I'll put an arrow on top of the 0 as a 0 vector. Means it's no rotation. There is no rotation. Or why don't we call it irrotatable? Yeah? Sure. I can't change these other ones, but okay. So what was I saying? Curl f equal to 0, no rotation, 0 vector, no rotation. irrotatiable. I suppose I was told that in the old days the curl is also known as the rot for rotation. Rot F describes a rotation. And positive, negative is kind of depending on your point of view. With two-dimensional vector fields, it's easy to determine whether something's positive or negative because you're really just focused on the last component because the first two components are 0. But your three-dimensional space, it's harder to deal with that. But it turns out that the magnitude of the curl, however, the longer the vector is, the faster the rotation. So the magnitude of the curl determines the speed of rotation. And the curl itself is a vector. It determines the direction of rotation. It's the direction of the rotation using your right-hand rule. Okay. So now we've established a couple of derivative, well, we've reestablished the gradient as a derivative of a scalar function. Now we have two different derivatives that we have defined for vector fields. We have the div and the curl. All right, let's see if we could steal some problems from your homework or something. Do I have your homework ready? Nope, I didn't log in yet. This would be section 15. Oh wait, these are integrals. So it's kind of weird. We're used to doing derivatives first and then integrals, but now when we're dealing with these vector fields, we jumped on the integral right away, and then now we're doing derivatives. Which I think is kind of lame. I thought maybe we should have done derivatives first. The curl should have been the first topic, the div and the curl, because really, I don't know. Oh, there's also a handful of other properties that'll probably be important, like in dealing with a function like this, where you have a scalar times x, y, z in the I, j, and k components. So there's some properties for the div and the curl where you can just take the scalars out, and it's like it's almost identical to the properties back in when we were dealing with just plain old vectors and plain old scalars. So let's try this one, the one with the I, j, k business on it. I mean, a scalar on the outside and the I, j, k. So we can think about this as just a function, a scalar function that we can move on the outside. And when we do the curl, we can multiply everything by the scalar function later on. So they asked for the curl first. Curl of the vector field. So we want the del operator cross the f function. And what I'm going to do is I'm going to look at f as some scalar times the I component, the j component, and the k component as a vector. So I'll just focus on the x, y, z vector and then work with that and then just multiply everything by star at the end. So the curl is going to be star. And then now I need to take the derivative of these things, combinations of these things, right? So do you remember that cross product in your head? So it's the partial of, the first one is the partial of q with respect to z, right? So we can establish which one's your P and your Q and your R. So the partial of Q with respect to Z is 0 minus the partial of R with respect to R with respect to Y, and then partial of Q with respect to Z. So that's going to be 0. The partial of R with respect to X, that's just Z, so this is 0 again, minus the partial P with respect to Z, this is 0 again. Looks like this is all going to be zeros. Conservative. It is. So remember they were talking about conservative yesterday, a conservative vector field, if those two things are equal. Well, that's the simple case in 2 dimensions. It turns out that if you get the curl and the curl is equal to 0, like in this case, then this is conservative. So that's a definition that we're going to write down a little bit later. But this is going to be the 0 vector, so we say that this vector field F is conservative. Remember that word yesterday, conservative? Yeah. Which means, if it's conservative, what is it from yesterday? What? Yeah, so if it's conservative, it is a it's a gradient field. It's a gradient field. All right, so this one turns out to be 0. Find the divergence of this thing. We'll use the same function, and then this time we'll take the dot product with a del operator. So again, the star is just going to be there. And so I'm going to want the partial of x with respect to x, partial of y with respect to y, partial of z with respect to z. So this is just going to be 3, but then you have this constant up here too, outside. So this is going to be 3 times star. 3 times 9 is 27 over this whole thing. So this is your div. Okay? So I wonder if you put 0 in there, if it's going to be okay with this. Or actually, it should be a vector field. The first one should be wrong because it needs to be a vector. I wonder if they're going to be okay with that. Is it partially?
What? Oh no.
What? What? Watch a video.
Actually, better we'll all go home, figure it out, and then bring back the answer.
No.
Nice try though, right?
No, it wasn't even a nice try.
Being yelled today.
Wow. Should we do another one? See if we get it right this time? I don't know what's wrong with the other one.
Look at that black square. Maybe that's.
No. Negative?
Oh yeah, try negative.
Why would it be negative?
Somebody else said that. I was just like, yeah, try that.
Oh well. All right, well, you guys can figure it out. So, quiz is a take-home quiz. Now, this is a little bit involved, and it kind of deals a lot with physics and stuff, but it began as something kind of similar to two of the things that we've been doing. One of our examples is negative y comma x as a vector field, and then the one that we just tried to do had a divided by x squared plus y squared. So when you do this, think about pulling the scalar function part out and just focus on a small, simpler vector field. Okay, so this particular quiz is broken up into three parts. The first part prepares you with what would go in your integrand when you're doing this line integral. So this is actually a few line integral problems. So the first one is asking you to figure out what the vector field is dotted with some curve. And what you need to do is you need to parameterize two curves here. One of them is a line that goes through the origin, 0, 0. And then the other one are circles, so radius, whatever the radius is, a. And so once you've figured out what the parameterization is, you just put that parameterization into the vector field, that would be b, and then you dot it with the derivative of your parameterization, whatever that is. That would be r prime. And then this part is what's going to go in your integrand when we start doing integrals. So it turns out that if you look at a radial curve, just a straight line going through the origin, and if you look at circles, they follow a certain pattern regardless of what the slope is or regardless of what the radius of the circle is. So when you go to the next part, there are six different curves that you're going to integrate over. The thing is, 4 of them are going to be circles or pieces of circles, and then the other 2 are line segments, radial line segments. So based on what you got from part 1, that should make your job a lot easier in part 2. So all you have to do is figure out limits of integration, looking at a circle or looking at the line segment that you're dealing with, and then that'll help you find those integrals. After you do that, and based on what you've done so far, they want to look for closed curves C7 and C8. So you're going to make up 2 new curves that are closed curves that, in this case, would have a integral that's non-zero over one of them, and it's equal to 0 over the other one. So you can see that according to the fundamental theorem of calculus or line integrals, a closed curve should be equal to 0, right? Well, something is not happening correctly here, where the fundamental theorem of calculus might not work. And according to Green's theorem, it's like doing the area of something. So that might also not work here. And then part B, there's Ampere's law that says on the closed curve, the integral is mu sub 0 times the current flowing through the curve, z. So this is a two-dimensional vector field. The z vector is going up. So what you would kind of do is kind of imagine a rod, a three-dimensional rod, but what you're focusing on is you're focusing on a flat plane that cuts the rod, and that's the two-dimensional picture that you should be looking at. So you're looking at a flat plane, imagining the rod coming straight at you from this point of view. And so that's what they mean by the z direction when they talk about the z direction. And then conservative, we just kind of semi-defined conservative today, and they talked about conservative yesterday using Green's theorem. So think about what that means, look at Green's theorem, and see how that relates to what it is we're talking about. Okay, so this is your quiz that's due on Monday at the beginning of class. Don't wait till the last minute to do this, because it's not an easy quiz. You have to go through the process of taking this step by step. Okay? All right, have a good weekend.